Hey everyone, and welcome back to the channel. Today, we're diving deep into the art and science of PCB design. Ever wondered what makes a good circuit board design truly great? A lot of it comes down to routing, how you connect all the components. Get it right, and your device works flawlessly. Get it wrong, and you're in for a world of headaches. So grab a coffee, and let's unravel the secrets of professional PCB routing, starting with the absolute foundation, component placement. Before you even think about drawing a single trace, you need to know where everything goes. Strategic placement is everything. Think of it like planning a city. You wouldn't put a loud factory right next to a library, right? Same principle here. Group your components by function. Keep your analog, digital, and power sections separate to prevent them from interfering with each other. This simple step can save you from a lot of noise issues later on. Next, think about the signal flow. Arrange your components so the signal can travel in a clean, direct path from input to output. This naturally helps minimize trace lengths. Shorter traces mean less delay, less resistance, and less opportunity for noise to creep in. Also, be mindful of sensitive components. You want to keep them far away from anything that's high frequency or high power, which can act like a noisy neighbor. And don't forget about heat. Place components that get hot, like voltage regulators or powerful processors, where they can get good airflow or connect to a heatsink. Good thermal management is key to reliability. Finally, make sure your test points and critical components are accessible. There's nothing worse than needing to debug a board and not being able to reach the point you need to probe. Once your components are thoughtfully placed, we can start talking about the connections themselves, the traces. The golden rule? Keep traces as short and direct as possible. Long, meandering traces can act like antennas, picking up noise and causing signal delays. You want to avoid creating unnecessary loops in your traces, as these can create inductance, which is another source of noise. For high-speed signals that need to arrive at the same time, like in a USB or HDMI interface, maintaining consistent trace lengths is crucial for timing integrity. We call this length matching, and it's a non-negotiable for high-performance designs. We're essentially making sure the signals win the race by finishing at the exact same time. Now, let's talk about the size of these roads, the trace width and clearance. It's not a one-size-fits-all situation. The width of your trace depends on how much current it needs to carry. A high-current path needs a wider trace, like a highway, to handle the traffic without overheating. For high-frequency signals, maintaining a consistent trace width is critical for managing something called impedance, which we'll talk more about in a bit. Just as important as the width is the space between the traces or clearance. You need enough space to prevent signals from jumping between traces, a phenomenon called crosstalk, and to avoid accidental shorts during manufacturing. Always, and I mean always, check your manufacturer's capabilities. They'll tell you the minimum trace width and clearance they can reliably produce. And if you're working with high voltages, there are specific safety standards that dictate the spacing required to prevent arcing. Safety first. This brings us to one of the most important concepts in modern electronics, signal integrity. This is all about preserving the quality of the signal as it travels from one point to another. First rule: avoid sharp 90-degree bends in your traces. These sharp corners can cause signal reflections, which corrupt your data. Instead, use 45-degree angles, or even better, smooth, curved traces. As we mentioned, keeping trace widths uniform is essential for maintaining controlled impedance, which prevents those pesky reflections. For high-speed differential pairs, like those used for USB, you must route them together, keeping their spacing and length perfectly matched. This helps cancel out noise. And try to minimize the use of vias, which are the little holes that connect different layers. Every via introduces a small change in impedance, so for critical high-speed signals, it's best to stay on one layer as much as possible. A solid, continuous ground plane underneath your signals provides a stable reference and a clear return path, which is fundamental for good signal integrity. Let's talk about layers. Modern PCBs are like multi-story buildings, and how you organize the floors or layers is critical. A great strategy is to dedicate entire layers to be solid planes of copper for power and ground. This creates a low impedance distribution network that provides stable power to all your components and excellent shielding. You can then sandwich your high-speed signal layers between these ground or power planes. This configuration, called a stripline, helps contain electromagnetic fields and dramatically reduces interference. Try to arrange your signal layers so that if they are adjacent, the traces run perpendicular to each other. This minimizes crosstalk. And just like with single traces, try to minimize how often a critical signal has to switch layers. Every layer change is a potential point of failure for signal integrity. Proper layer stack-up planning is a balancing act between signal integrity, thermal performance, and cost, but getting it right is a game changer. Vias deserve their own special attention. While they're essential for connecting layers in a complex design, they can also be a source of problems. As a general rule, use them sparingly, especially on high-speed signal paths. Each via adds inductance and capacitance, creating an impedance discontinuity that can degrade your signal. However, for power and ground connections, don't be shy. Use multiple vias to create a low-resistance connection between your planes. This also helps with thermal management, as vias can act like little pipes to draw heat away from components. We call these thermal vias. In high-density designs, you might see via in pad, where the via is placed directly on the component pad. This saves space but requires a special manufacturing process to fill the via and prevent soldering problems. Always be sure to follow your manufacturer's guidelines for via sizes and annular ring requirements to ensure your board can actually be built. Power and ground distribution is the lifeblood of your circuit. We've already mentioned using dedicated planes, which is the best-case scenario. If you can't afford that, use a star grounding topology where all ground connections meet at a single point. This helps prevent ground loops, which can introduce a ton of noise into your system. Keep your power and ground paths as short, direct, and wide as possible to minimize voltage drop and inductance. And here's a tip you cannot ignore: decoupling capacitors. These small capacitors must be placed as close as physically possible to the power pins of every single integrated circuit. They act as tiny local reservoirs of energy, filtering out high-frequency noise and providing the instantaneous current that chips need to switch states. A good decoupling strategy is your first line of defense against a noisy, unstable power supply. All of this work helps us fight two big enemies: crosstalk and electromagnetic interference, or EMI. Crosstalk is when a signal on one trace couples onto an adjacent trace, and EMI is when your board radiates noise or is susceptible to external noise. To combat this, maintain adequate spacing between traces, especially high-speed ones. Shield sensitive signals by routing them between ground planes or by using guard traces, which are grounded traces that run alongside the signal trace. Route high-speed differential pairs tightly together to leverage their noise-canceling properties. And always be looking for ways to minimize loop areas. The area enclosed by a signal trace and its return path acts like an antenna loop. The smaller the loop, the less immediate it will radiate and receive. So, with all these rules, where do you start? You need a routing order. Always route your most critical signals first. This includes clocks, high-speed data lines, and sensitive analog signals. Give them the shortest, cleanest paths possible. Once they're locked in, you can route the power and ground distribution network. After that, move on to less critical signals, filling in the gaps. Routing in groups based on function can also help keep things organized and minimize crosstalk. Following a logical order ensures that your most important signals get the priority they deserve. Finally, before you send your design off to be manufactured, you must run a design rule check, or DRC. Your PCB design software has a powerful, automated tool that checks your layout against a set of rules you define. These rules include your manufacturer's constraints, like minimum trace width and spacing, as well as electrical rules for your design. The DRC will catch errors like traces that are too close, shorts between different nets, and violations of manufacturing tolerances. It's your final safety net. Running a DRC is not optional. It's a mandatory step that will save you from costly and time-consuming mistakes. A clean DRC report is the final confirmation that your meticulously planned layout is ready for the real world. And there you have it, a comprehensive tour of the key techniques for professional PCB routing. From component placement to the final DRC, each step builds on the last to create a robust, reliable, and high-performance design. It might seem like a lot to remember, but with practice, these principles will become second nature. Thanks so much for watching. I hope you found this guide helpful. If you learned something new, please hit that like button. And if you want to see more content like this, make sure to subscribe and turn on notifications. Got any questions or your own favorite routing tips? Drop them in the comments below. Until next time, happy designing.